Hello everyone. Today we're going to be doing Lagrange multipliers. So you might remember last video we found minimum and absolute minimums and absolute maximums using like on constrained curves, right? So we had some kind of curve or some surface, I guess, in the XYZ plane. And then there was some kind of, let's draw that out. And yeah, there was some kind of constraint. And in this, like in the region of this constraint, we had to find the absolute minimums and absolute maximums of the curve. And the reason we didn't do any practice problems is because all of the exam problems that they have on boiler exams or past exams that depend on this kind of finding an absolute min or absolute max on a constrained curve are going to be solved, and they're best solved with the method that we're going to be doing today. Yeah, so you can completely forget about what happened last lesson, but this is generally the best way to go when it comes to finding mins and maxes on constrained curves, and that's Lagrange multipliers. So what this this entire lesson depends on a relationship that goes a little something like this: the gradient of f being the function that you're constraining, is equal to lambda, a constant, times the gradient of g, which is the gradient of the constraint you've been given, which is really interesting relationship. And I actually made a complete, well, I mean, the contours aren't, I didn't make the contour part, but I added some of my own curves to kind of get this point across. So our constraint is this circle, x squared plus y squared equals 4. And the curve, this yellow curve with these contour lines on it, that's xy plus 1, z equals xy plus 1. And I took the gradient. Okay, so before we get into these vectors right here, if you look at this guy from the top, you could see that this contour line right here passes on the, it's like a tangent to our constraint curve, okay? And what we also know is, so this level curve of our curve xy plus 1 is tangent at some points, is tangent to the constraint curve. And another thing we know about level curves is that the gradient vector is perpendicular to level curves of any function. So since they're tangent at that point right there, that means their gradient vectors are parallel, okay? And that means they're scalar multiples of each other. So these are literally the raw gradient vectors of each of the functions, and you could see that they're parallel to each other, and one is like, it looks like it's about double the other one, which is pretty interesting. So you could imagine that for any kind of constraint and for any kind of curve that or surface that you're constraining, the surface that you're constraining has infinite number of contour lines going all around it, and one of those contour lines is gonna hit your constraint just like this. And at that point, you could use this interesting property and write down this equation that I wrote right here and figure out that min or max. So yeah, now that doesn't account for saddle points like this, but for on the boundary, it's gonna work nicely. So yeah. Okay. So using that property, we could actually find it. I did find this earlier. That's how I even got the gradient vectors for this plot. But so we have the equation is z equals xy plus 1, and then our constraint is x squared plus y squared equals 4, right? So yeah, this is always going to be in the form of g of xy, a function of x and y equals a constant. In this case, that constant's 4. And this one is always going to be, you could always write it as, I guess, if you isolate this, if you move z to the other side, you would have a function of x, y, z, x, y, comma, z equals 0. So that's kind of how you could identify your constraint and your non-constraint curves. Yeah, okay, so the gradient of f, the partial in the x direction is going to be, let's see, that's just going to be y. In the y direction, that's just going to be x. And now the gradient of g is 2x, and then 2y. Okay, and then we use this little property right here, and we'll get that y equals 2x times lambda, and x equals 2y lambda. Now, funny part about these is we almost really never find what lambda is. What we're aiming for is a relationship between x and y. So we could, using both of these equations, I say that lambda is equal to y over 2x, and lambda is equal to x over 2y, okay? And that means that y over 2x equals x over 2y. And now you could just do cross multiply, you get 2y squared equals 2x squared. So y squared equals x squared. So y equals plus or minus x. Okay? So if y equals plus x, then you're going to get x, or you're going to get, oh, yeah, if y equals plus x. So, okay, so what you do with this result is you plug it into your constraint. Because you're using this constraint and the relationship you found to see where you could lie on the boundary, okay? So if y equals plus x, then you'd have 2x squared equals 4. So that means x squared is 2. So x equals plus or minus root 2. If y equals negative x, then you're going to get the same thing because you're squaring them. So you're going to get that x equals plus or minus root 2. So that gives us 4 points, which does align with what we see here, right? We have this point right here, we have this point, and then we have this point, and then this point. It's kind of like a saddle point shape. Actually, that's exactly what it is. See? Okay. So, and now after this, maybe not exactly for this problem, but it can get a bit chaotic. You kind of have to run down like a different path. So we start here, we say, okay, if y is plus x, then we go down this path, and we get that x is plus or minus root 2. If x is plus root 2, then y is also plus root 2. Okay, so this is one of our points. A min, a max, I don't know. We could check that later. Okay, now, again, let's do it again. If y is plus x, we move down here, and then x is minus root 2 this time. Okay, but we said that x is plus x as well, so x is, or y is going to remain negative root 2. Okay, and now we could do it again, but with minus. So if y is negative root x, or if y is negative x, then we go down this path. And again, we get that x is plus or minus root 2. So let's choose plus root 2. Okay, but y is negative x, so y is going to be negative root 2. And if we do the other one, if we say that x is negative root 2, y is negative x, so it's going to be just positive root 2. And then you could plug these 4 points into this function and get the z value and get your min and maxes. So yeah, I'm not going to plug them in, but this is what you would plug in. So yeah. Let's see, could we get any more difficult than this? It's not terribly difficult. We can also look at an example that we could also just jump straight into problems. I don't think this is more algebra, honestly, than calculus. You kind of just plug them into this formula, and then for different problems, you'll have different methods of doing like algebraic manipulation to get an actual relationship. But we could honestly just jump straight into problems. It's not the craziest derivation. It's hard to see if you're starting from nowhere, but okay. So this is a test problem, a past exam problem. Use the method of Lagrange multipliers to find the x components only of the points where the absolute max and min occur. So they tell us f of x comma y equals x minus 2 squared plus y minus 4 squared on the curve x squared plus y squared equals 5. Okay? So this is our constraint, and then this is our function that we're constraining. So gradient of f, I guess the fastest way to do this is, I'll take it slow, it's fine. The gradient of f is, well, this whole term is y, so we don't care about that. It's going to be 2 times x minus 2, and then in the y, it's going to be 2 times y minus 4. And then gradient of g, our constraint curve, is just 2x comma 2y. Cool. All right, so now we use the relationship of gradient f equals lambda times gradient of g. And we could turn this into 2 times x minus 2 equals 2x lambda. And then 2 times y minus 4 equals 2y lambda. Cancel these 2's out. And I do like using this approach of finding what lambda is on each equation and then equating them. So you're going to get that lambda equal, for this first equation, you're going to get lambda equals x minus 2 over x. For the second one, you're going to get lambda equals y minus 4 over y. And then you can equate these, x minus 2 over x equals y minus 4 over y. Cross multiply, you're going to get xy minus 2y equals xy minus 4x. Cancel out these xy's, and you're going to get that y equals 2x. Okay. Another quick tip is sometimes you can miss it, but when you set up this equality, you could tell right off the bat that if you put x equals 0 or y equals 0, it's going to be a solution. Hopefully we see an example later that's like that. But be wary of that, because sometimes you could skip over a solution. Okay, but not in this case, right? If we put x is 0 on both sides, we're going to get negative 2 equals 0, and that's not true. So 0 is not a solution here. Okay, so y is equal to 2x. That's our relationship between x and y. That means we plug this guy back into our constraint to get what they have to equal, right? So if y equals 2x, you're going to get x squared plus 4x squared equals 5. So that's 5x squared equals 5, so x squared equals 1, so x equals plus or minus 1, okay? So if x is plus 1, then y is 2 times that, so it's just going to be 2. If x is minus 1, then y is just going to be negative 2. Okay? Okay, and the problem asked to find the x components only of the points where the absolute max and min occur. So we only have 2 points, and we have 1 and minus 1 as our solution. So we're gonna, yep, that's right. Okay. Let's see. Okay. Or should we do this one? Should we do one that hopefully might have 0 as a solution? That's not going to have 0 as a solution. Nope. 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 Okay, we can try this. So this just says find the minimum value. So min of f of xy equals x plus y, subject to the constraint of, I'll just write it as g of x and y, which is 0, which equals x squared plus 2y squared minus 6. Okay, so gradient of f, this one's pretty easy, it's 1, 1. Gradient of g is 2x, comma 4y. Okay, so this one's going to come out pretty nicely as well. And the next problem is the hardest that I think these could get. So here you're going to have 1 equals 2x lambda, and 1 equals 4y lambda. And as I like to do, I like to isolate lambda. So I get that 1 over 2x equals lambda, and that 1 over 4y also equals lambda. Okay, now I equate these. So you're going to have 1 over 4y equals 1 over 2x, right? And then if you cross multiply like that, you're going to get 2x equals 4y, so x equals 2y. Okay, and then you take this guy, plug him into your constraint, and you're going to get, so 6 equals 2y squared plus 2y squared. That's a really weird way to phrase it, but this is 4y squared, right? 4y squared plus 2y squared, that's 6y squared. You can cancel out the 6's, and you get that y equals plus or minus 1, okay? So if y is plus 1, then x is going to be 2. If y is minus 1, then x is going to be negative 2. Okay? So let's see. So we want the minimum. So yeah, it wants the minimum value of f of xy. So it's going to be neither of these. What we have to do is plug them back in here and see which one is a smaller value. So f of 2 comma 1 is 2 plus 1, which is 3. And then f of negative 2 comma negative 1 is equal to negative 2 minus 1, which equals negative 3. So obviously between these, negative 3 is the smallest number. So, yep. Okay, and then this next problem is the most difficult that you could get. So another, I'm not going to toy around with this another method to do this problem, but I can mention it. Okay, but first let's look at what the problem is. So it says the shortest distance, from 1, 1, 0 to the plane x plus y plus z equals 1 is boop, boop, boop. Okay, so this is at first really weird problem to look at, but what you have to use for this problem is the distance equation. So the distance function, which is really a function of 3 variables, and then we'll just square it for convenience sake, is going to be x minus x naught squared plus y minus y naught squared plus z minus z naught squared. Okay, and then what was it? Yeah, so this is our function, and we're trying to minimize this function, right? We want the shortest distance, so we're trying to minimize this function using this constraint, x plus y plus z equals 1. So this is our constraint, and then this is the function we're constraining, okay, the distance function. Now the alternative method I was thinking of is I could draw it up here. So yeah, the alternative method is you have a plane, right? This is, suppose this is x plus y plus z equals 1. I know it's not, but suppose it is. And then, I don't know, this is the point we're observing, 1, 1, 0. You could treat this guy as a vector, and then project, you could project this guy onto the plane, and then subtract this vector and its own projection, and you'd get this displacement vector, and then you could find the magnitude of that displacement vector, and that would also give you the same answer. We can verify it after, but I haven't projected stuff in a while, so I can try. But okay, let's see, or I'll probably try that off video just for sanity's sake. If you want, I can upload that method as well, but I have to, you have to review my projections. Anyhow, yeah, so if this is our f, the thing that we're constraining, gradient of f is going to equal, oh yeah, note that because we squared it, at the end we're going to have to square root our function in order to get the right answer, but I really don't want to deal with this square root on this side right now, especially while I'm doing these algebraic calculations. So I'm just rewriting it this way. Okay. So gradient of f is going to be 2 times x minus x naught. X naught in this scenario is 1. Okay, and now y is 2 times y minus y naught, which is 1. And then z is going to be 2 times z minus z naught, so which is just 2z. Okay, and the gradient of g is 1, 1, 1. 1, 1. Well, hold on. This is, yeah. Okay. Yeah, 1, 1, 1. Okay. Okay. I don't know why that makes me a little bit uncomfortable. Yeah. Okay. So now let's solve this. So you have gradient of f equals lambda times gradient of g. So you have 2 times x minus 1 equals lambda. Okay, and then you have 2 times y minus 1 equals lambda, and then you have 2z equals lambda. Okay, so based on this relationship, the fact that 2x minus 1 is lambda and that 2y minus 1 is lambda, you can conclude that y equals x. Okay, and then you could plug one of these guys in, so you have 2z equals lambda, but lambda is also equal to 2 times x minus 1. Okay, so then you can cancel these out. You get that z is equal to x minus 1. Okay? Okay, so these are our relationships. We have that y is equal to x and that z is equal to x minus 1. Okay? So we want to plug these back into our constraint. So x is just going to remain as x. Y is equal to x, so we could replace that with x. And then z is equal to x minus 1. So you could do that, and that all equals 1. Okay, so you have 3x equals 2, and x equals 2/3. Okay, y is equal to x, so y is also 2/3. And then z is 2/3 minus 1, so that's negative 1/3. Okay, all right, so now we have these points, and we're going to put these guys back into our distance function. So x minus x naught, so you have 2/3 minus 1, and then you have 2/3 minus 1 again. Oh, you have to square these. And then plus z, which is negative 1/3 squared. Okay, and this equals our distance squared. Okay, so 2/3 minus 1 is minus 1/3 squared, that's 1/9. So all of these are 1/9. So 3 times 1/9 is 3/9, which reduces to 1/3. And 1/3 is d squared. Take the root of both sides, you're going to get 1/√3 equals d. And then you can rationalize that and get √3/3 as your answer.